I want to explain about the star clusters. Let me share my screen. Yeah. Here you see different colors, and here we have iron over hydrogen. But for helium, for example, some scientists said that the cause of the difference in helium abundance in globular clusters is that different globular clusters merge to each other already. Here you see it is in ultraviolet, and we see different multiple populations in globular clusters. Here it is reddening determination also works for these indices, not only for U minus B versus B minus V. You see again, it is in ultraviolet. We have different populations. And for red giant branch, for example, we have population 1, population 2, and their density is different. For example, the helium is different abundance, and so here we have, for example, 3 populations. Here, individual populations, very different characteristics. For example, 2 population, 2 population, 2 population. You see different population. Results for all the star clusters and also in the small Magellanic clouds, and that we can say that in globular clusters in our Milky Way, and also all clusters in other galaxies, for example, in small Magellanic clouds and large Magellanic cloud, we can say there are different populations, but not in open clusters. They are just in old and globular clusters, but not in open clusters, which they are young. Also, you see, in a small Magellanic cloud, also we have different kinds of population, but their age are very high and they are old. Here you see different kinds of population in small Magellanic cloud. 3 populations here. Also here we have 2 mix. Or also here you can see. Also here we have 2 populations. As you see, also we have merge here. Intermediate black holes in globular clusters, as seen since for massive black holes, the mass of intermediate black holes is around 100 to 100,000 solar mass, important for information and evolution of galaxies, detection via kinematics of central globular clusters, stars, or X-ray emission from the center due to accretion of gas. And because the accretion disks of pre-main sequence and black holes have X-ray emission, because we can detect the central globular clusters, and also we cannot dissolve the center of the globular clusters, and there is a poor resolution and there are different X-ray emission, we cannot detect intermediate black holes in the globular clusters. Also, there are some literatures that you can see. Here we have intermediate black holes in globular clusters, elements of a black hole, accretion disk, a swirling mass of matter destinated destined to spiral into the black hole or be ejected into space. Relativistic jets, matter and radiation extending out hundreds of thousands of light years. Even event horizon, gravitation boundary beyond which neither light nor matter can escape. Stars close to the intermediate black holes should accelerate. What is needed for globular clusters? Total mass, the ratio of disk luminosity and star mass around it, distance and model for the kinematics after many gigayears, and then look for anisotropy and kinematics from Hubble Space Telescope or Gaia. And here you see intermediate black hole globular clusters, fraction of black holes that are inside a certain radius, and the velocity distribution of stars within 20 arcseconds of the center of omega century. Shown is the one-dimension velocity distribution for the stars with measured proper motions by Bellini et al. Black dots. And the best fitting n-body model with an intermediate black hole blue dashed line with 10% and 75% black hole retention fractions, black dots dotted and red solid line. And the model with a high retention fraction of stellar mass black holes provides the best fit to the observed distribution. Here you see no black hole, and black is radial velocity, orange is proper motion. We can say that at the beginning of evolution of globular clusters, stars evolve as single stars. So when there are supernova, they didn't merge to each other to be massive and make black holes. So we don't have black holes in globular clusters. You see here intermediate black hole in globular clusters, and we can say that the differences of the list of cluster parameters from the literature, you see the stellar parameters are important: distance, mass, and luminosity. And the result is there is no evidence for an intermediate black hole in Omega Centauri. The rotation of globular cluster, rotation as the solving mechanism for globular clusters, and Salima and et al. They said that 15 of 62 investigated globular clusters are rotating, used radial velocities and proper motions. Cordoni and et al. Said that 2 of 6 investigated globular clusters are rotating, used radial velocities and proper motions, and analysis of 2 different internal populations. And the globular clusters rotate, but open clusters do not rotate. On the center of gravity, the hypothesis is, for example, 2 globular clusters merged in the past. So we have different helium sequences. Then the movement is the cause of rotation, but it's not 100% for certainty of that. Here you see both populations, 1 and 2 seem to rotate differently only on 2.5 sigma. As you see, it is for population 1 in red and population 2 in blue. Also here you see rotating globular clusters. Different references find rotation or not for the same globular cluster, but mostly most of them have a rotation. By general, for globular clusters population 2, we can say that they have more metal than some, and they are older than globular cluster population 1, and their metallicity are different, stars in different evolution, and their cores are dense and has a lot of sequences and has a lot of stars. There is no intermediate black hole in the center of globular clusters, and they have different sequences. Almost all the globular clusters rotate. Population 1 is the galactic halo, is in galactic halo, and population 2 of globular clusters are in galactic bulge, that they are old. Extragalactic star clusters. Star clusters are found for almost all galaxy types, either globular, so far away from the disk or center, or star-forming regions, bright, observed, for example, NGC 5128, elliptical, about 1,600 globular clusters it has. And in NGC 628, spiral galaxy, and it is complete young cluster population. M31 Andromeda galaxy, it has 1,200 globular clusters, and here you see the Large Magellanic Cloud. It has 6 degrees on the sky in the northern hemisphere. And here it is a Small Magellanic Cloud with 5.4 degrees on the sky of south hemisphere. The gravitation pull of the Milky Way caused the Large and Small Magellanic Clouds to be irregular galaxies and not be spiral galaxies. And this gravitational pull is much more in Large Magellanic Cloud than in a Small Magellanic Cloud. As you see, it is more irregular than this one. Tahereh Ramezani is a star cluster in the Large Magellanic Cloud. It has 4,850 stars in it. And here you see open clusters in the Milky Way. In the Magellanic Cloud have the same morphology as globular cluster in the Milky Way. It is a globular cluster in the Milky Way, but it is an open cluster in Magellanic Cloud. In Large Magellanic Cloud, the age of this is about 100 million years, but the age of this globular cluster is about 15 gigayears. It is in Milky Way and it is in Large Magellanic Cloud. So because of this, in irregular galaxies, we do not call open clusters or globular clusters, we call all of them star cluster. Because the morphology of them is somehow similar to Milky Way. And because of them, it is, but it is open, but it is globular. It is young, but it is old. So we call all of these as star clusters, not separate them into open clusters or globular clusters. Distance and reddening in Large Magellanic Cloud, it is 18.5 magnitude. It has 0.05 to 1 to 0.5 magnitude, and its distance is about 50 kiloparsec. But in a Small Magellanic Cloud, the absolute magnitude is 19 magnitude. Reddening is or extinction is 0.05 to 0.1 magnitude, and the distance is about 60 kiloparsec. Intrinsic reddening up to 0.2 magnitude for normal regions in the bulge. Characteristics are irregular galaxies disintegrate because of gravitational interaction with Milky Way, and global elemental abundance is lower than in the Milky Way. The ratio of iron to hydrogen is about -2 to -0.3 dex. Total mass is about 20 times lower than in the Milky Way, and global magnetic field lower than in the Milky Way. Here you see the difference and the distance of them. In large Masaryk cloud is 7 parsec, but in small Masaryk clouds it is 20 parsec. And here we can see the diameter of around 1,762 of star clusters in large Masaryk cloud is less than 20, the percentage of star clusters. Most of them are until 20 parsec. It is similar to our Milky Way that most of the star clusters are until 20 parsec, but it is somehow by chance. They have no relation to each other. Impact for the study of star clusters in the Masaryk clouds. The diameters of star clusters are normally below 1. The core regions are difficult to resolve. The distance is no free parameters anymore. There are almost no foreground objects. The membership determination on a kinematical basis is almost impossible, and star clusters are most suitable to perform statistical investigations. Thank you for your attention and see you next time. Bye.